We've reached Unit 8, our last unit. In this section we are looking at, or in this unit we are looking at sequences, a little bit with series and the binomial theorem. We're going to start with sequences and series in this first section. Objectives here are to find particular terms of a sequence from the general term, write the general term of a sequence, and understand series and summation notation. Just a little bit of introduction to this here. It is important that we study numbers to try to learn from them. Investment bankers look at historical data, stock prices, interest rate, currency exchange rates to estimate how financial markets might change in the future. Scientists use past earthquake data to predict future earthquake patterns. Police departments use past crime data to predict when and where future crimes may occur. Sports analysts use previous performance to predict future player or team success. And I could go on and on and on and on, right? I just picked like a variety of different things. These are all very complicated situations. They have a lot of, quote, moving parts, which are variables. They require more expertise in those particular areas. But what we are going to look at, or what the idea here is, and the reason I mention these things, is the idea of looking at some sort of pattern in the data and maybe trying to make predictions based on it. That's the idea behind a sequence, is looking at this pattern, or this pattern of numbers. A sequence is a function where the domain is the set or part of the set of natural numbers, usually starting with 1. Natural numbers 0, 1, 2, 3, and so on. It's an infinite sequence if the domain is the whole set of natural numbers, and finite if the domain is part of the set of natural numbers. It could also be infinite if it's a part of the natural numbers that maybe just don't include a few terms at the beginning. So like if you started at 1 and went, oh my goodness, this isn't right. Natural numbers start at 1. Oh, my brain. Whole numbers start at 0. Sorry about that. So, if you have part of the natural numbers, you start at 3 or something and still go on forever. It's still an infinite sequence. Let me show you what I mean here. We are talking about the domain being natural numbers. We only want to plug in these positive integers. So for example, we could say a of 1 is 2 times 1 plus 3, or 5. A of 2, 2 times 2 plus 3, or 7, and so on, right? Because we only are plugging in natural numbers, we don't typically use the function notation there. It would be much more common to write a with a subscript of 1 equals 5. A with a subscript of 2 equals 7, where that subscript, it corresponds to that natural number that you're plugging in. Here's another example. A sub n, so now instead of using the function notation, I kind of wanted you to see that function notation to recognize these are functions. We're just very restricted in what our domain looks like. Here, much more common would be to write it this way. A sub n equals n cubed. That means a sub 1 is 1 cubed, or 1. A sub 2 is 2 cubed, or 8. A sub 3 would be 3 cubed, which is 27. A sub 4, 4 cubed is 64. And a sub 5 is 5 cubed, or 125. It's also very common to write these as a list of numbers with brackets like that. This a sub n is called the general term of the sequence. A sub n equals n cubed is the general term there. I wanted to look here. I think it's important to know graphically what is happening. So I did include a graph here of this sequence. Let's figure out what the first 3 terms are. A sub 1 is negative 1 to the first over 2 to the first plus 1. Negative 1 to the first is negative 1 over 3, so negative 1/3. Then a sub 2 will be negative 1 squared over 2 squared plus 1, just like a function. Everywhere you see the n, you replace it with, in this case, 2. That's positive 1 over 5. A sub 3 would be negative 1 cubed over 2 to the third plus 1, which is going to be negative 1 over 9. And so on. You could keep going. I'm going to do one more just to make sure we see the pattern that's going on here. 2 to the fourth plus 1. That's 1 over 17. What you have in this picture is the graph of this sequence. It is important to recognize that we do not connect the dots here. The reason we connect to the dots on something like a line is because our domain for a line is all real numbers, meaning you can plug in fractions between 1 and 2, right? You can plug in 1.5 or 1.2357 or 1.9996 or whatever. You can plug in numbers between the integers. That's what connecting the dots really does, is it's really a bunch of dots that fill in all those spaces. With a sequence, that is not true. You are not plugging in values between the natural numbers. You're only plugging in the natural numbers. What we have here, negative 1/3 would be down at negative 0.3. I did not, the graph was too far out. You couldn't see it if I showed you that whole thing. So I didn't do that here. Notice the scale here is by 2s. If this is 10, we're at 2, 4, 6, 8, 10. This is 2. So when, in this case, would be the n-axis and the a-axis. When n is 2, we're up here at 0.2. That's this 1/5. N is 3, halfway in between the 2 and the 4 there. We're down here. 1/9 is 0.1 repeating. So that is that negative number. Then this 1/17 would be here when n is 4, and so on. If you notice what's happening, the a sub 1 would be way down here. This is sort of bouncing back and forth between positives and negatives, right? That is because of this negative 1 to the n power that we have. When n is even, you'll get a positive. When n is odd, you will get a negative. Because it changes between positive and negative, we call it an alternating sequence. It's also interesting to note that as n increases, these values are going to get closer and closer to 0. Because your numerator will always be 1 or negative 1. The denominator is going to blow up. So when you have that big denominator, it's going to get closer and closer to 0. We're going to go the other way now. I gave you a sequence here, and I want to look at the general term of that sequence. Remember, this corresponds to n equals 1, n equals 2, n equals 3, n equals 4, n equals 5 here. So we need to think about the relationship between 2 and 1, 4 and 2, 8 and 3, and so on. This a sub n, what if I do 2 to the n? This is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, right? I think that is a appropriate general term here. We only have 5 numbers. It could go wonky after that. The 6th number might not be 64. We aren't really guaranteed this, but it seems to be the pattern that is happening. The next term, by the way, this is what we call a geometric sequence. We're not going to go into huge details about those, but that is called the geometric sequence, where you multiply by, as n increases each time, you multiply by another number. From here to here, we multiply by 2. we multiply by 2, we multiply by 2, we multiply by 2. Let's take a look at this next guy. I have an alternating thing here, so that means my b sub, I'm going to call it b sub n, has to have a negative 1 to the n in it. The alternating, by the way, will always be negative 1 to the n or negative 1 to the n plus 1. It depends what you start with. N equals 1. If you need your first term to be negative, you have to use this guy. If you want your first term to be positive and then the second term to be negative, excuse me, you have to use this guy. So this takes care of the alternating part. Now we need to deal with the 3, 6, 9, 12, and so on. So we're talking about n equals 1, 2, 3, 4, 5. What's the relationship between 1 and 3, 2 and 6, 3 and 9, 4 and 12, 5 and 15? To me, that seems like 3n. Right? When n is 1, 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5. This would be what we would call an arithmetic sequence. It's alternating arithmetic, I suppose, where each time, ignoring the alternating for a second, assuming that wasn't there, each time you're adding the same amount. So geometric, you multiply by the same amount from term to term. In this case, 2. Same value. Arithmetic, you add the same value. So kind of ignore the alternating. Technically, I guess this isn't arithmetic because of that alternating, but add the same value. You keep adding 3 there. Factorial notation. N factorial is the product of all positive integers from n down through 1. So 1 factorial means 1. That's it. 2 factorial is 2 times 1, or 2. 3 factorial means you just multiply all the integers from, or the natural numbers, positive integers, from that number on down, which is 6. 4 times 3 times 2 times 1 is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. That is something that commonly shows up in sequences, so that's why we're talking about factorial notation here, like this one. Find the first 5 terms of this. B1, 2 to the first over 1 factorial, is 2. B2 would be 2 squared over 2 factorial, which is 4 over 2, or 2. B3 is 2 to the third over 3 factorial, which is 8 over 6, or 4/3. B4 would be 2 to the fourth over 4 factorial, which would be what, 16 over 24, which is 2/3. B to the fifth would be 2 to the fifth over 5 factorial. 2 to the fifth is 32. 5 factorial is 120. Those are both at least divisible by 8. 4 over 15. Yeah, that's it, right? Okay. So those are my terms. I guess I could write them here as a list. 2, 2, 4/3, 2/3, 4/15. And it will keep going. So that's dealing with a factorial in your series notation there, your general term. One other thing I do want to just introduce you to is this series or summation notation. A series is the sum of the terms of a sequence. So if you have a sub n in a sequence, and the corresponding series looks like this. This is the capital Greek letter sigma. This k equals 1 tells us where to start as far as plugging in k. And n, this number on top, tells us where to stop. The sigma tells us to add those numbers up. For this sequence, I'm just looking here, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. That appears to be 2n, right? A sub n equals 2n. Because this bottom row, the actual sequence is 2 times the n values. We need to know that general term because that's what is going to go inside this sigma notation. If we wanted to add 2 plus 4 plus 6 plus 8 plus 10 plus 12, we use our sigma notation. It doesn't really matter what you use down here. I, j, and k are common. So you might see something like I equals. I'm going to start at 1. If I use I there, I have to use I on the inside there. That becomes your sort of variable that you're replacing these numbers. Because this stops when I equals 6, we would put a 6 on top. This means plug in 1 to give you 2. Plug in 2 to give you 4. Plug in 3 to give you 6, all the way up until plugging in 6. That's where we stop. That gives us the 12. The sigma tells us to add all those numbers up. So that's a series. Finding this sum means 1 squared plus 2 squared plus 3 squared plus, I stop at 4 squared. 1 plus 4 plus 9 plus 16 would be 30, right? These are 10 and that's 20, so that's 30 total. Here's another one. When k equals 1, we have negative 1 over 1. Plus, when k equals 2, we have positive 1 over 2. Plus, when k equals 3, it'd be negative 1. Oh, shoot. Negative 1 over 3. Plus, when k equals 4, it's 1/4. When k equals 5, it's negative 1/5. When k equals 6, I get a positive number from negative 1 to the 6th. And then negative 1/7. Negative 1 plus 1/2. Sometimes my brain gets ahead of my pen. Negative 1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6 minus 1/7. Bless you. We could get a common denominator here. I'm just going to quickly throw this in my calculator. Maybe sort of quickly. This is not a quick process here. See if I can switch that to a fraction. There we go. Negative 153 over 140. Nice round number. Okay. That's how we use our summation notation. Let's do a couple more here. We want to go the other way. So in these examples, I gave you the sigma notation, and we figured out what the sum was. Now I'm giving you the sum. I want you to write the notation. That means we need the general term. 3, 6, 9. Remember, this is talking about n being 1, 2, 3, 4, 5, 6, 7, and 8. That appears to be 3n. Generally, you're going to see I, j, or k here. Starting at 1, going to 8. That's it. All right, if we have an infinite series, we use an infinity symbol as our top index. So up here, because we have these ellipses for the dot, we are going to use infinity up here. Let's just to switch it up a little bit. Let's say J. I'm alternating here. Specifically, I'm alternating starting with the positive. So if I start at 1 here, I'm going to have to do J plus 1 so that when I plug in an odd number, I actually get an even exponent. So when I plug in J equals 1, I get -1 squared, which will give me the positive. Then when I plug in J equals 2, I will get -1 cubed, which will give me this negative that I need here. Remember, we're talking about J or N or whatever you want to use being 1, 2, 3, 4, 5 here. What's the relationship between 1 and 1, 2 and 8, 3 and 27, 4 and 64, 5 and 125? That's the cube, right? Each of those is the cube of the J value. Because we have the ellipses here, it goes to infinity. That's an infinite series. That really is the extent of what we're going to talk about with sequences and series. There is a lot more that we could talk about, but for this class, I think just introducing that notation, understanding what these ideas are, is sufficient. We've talked about a lot this semester, so I'm good with just introducing this notation to you.